Good morning, students. Let's wait for 1 or 2 minutes because I can see only couple of them are there. Okay. Once again, good morning, students. So in yesterday's session, we have discussed about Unit 1 revision, and we understood about the important questions of Unit 1, and I also said how you need to answer for so and so question. So today we are going to continue our discussion on Unit 2. So in Unit 2, compulsory one guaranteed question is a CPU scheduling problem. So definitely you can expect one problem on CPU scheduling algorithms. So they might be giving some numbers representing the burst times, and you might be asked using certain scheduling algorithms. You will be asked to calculate the average waiting time and average turnaround time. So I'm sure that all of you are confident to solve the problems without arrival times. Some of you might be facing difficulty for calculating the average waiting times and average turnaround times if arrival times are given. So you need to solve more and more problems in order to accurately calculate the average waiting time and average turnaround time when arrival times are given. So you need to solve more and more problems if arrival times are given. So I'm going to quickly show you one of the example with arrival times being considered. So without arrival times, I hope all of you are confident. So anyway, coming to the PPTs that I have said you, so you need to refer chapter 5, chapter 3, chapter 6 and chapter 7 PPTs. These 4 PPTs comprise of this unit 2 syllabus. Whatever our unit 2 syllabus is there, that is process management, which includes the concepts of process and CPU scheduling algorithms. They are included in chapter 3 and 5, and concurrency and synchronization are included in chapter 6 and 7 PPTs. Even the same in the Galvin textbook also. So the long questions that you can expect from these two chapters are, as mentioned, one is the CPU scheduling algorithm, and the other one is the pseudocode you should learn for the synchronization problems. We have already discussed the classic problems of synchronization, that is the producer consumer problem, readers writers problem, and the dining philosophers problem. These are the three classic problems of synchronization we have addressed. So for all these three, using semaphores and monitors, you should be aware about the pseudocode. I'm not asking you to remember the entire program, just the pseudocode. So compulsory with pseudocode explanation is required for these three problems using semaphores or monitors. So both are very important, and if you are lucky enough, you might be just getting the question from using the Peterson solution. So Peterson solution is also the classic problem of solution for the race condition. So that also you should be familiar with the Peterson solution, the structure of one single process you should be learning. So that is there. Yeah, here you can see the Peterson solution. Yeah, this is the simple pseudocode that you can just remember for the Peterson solution. Yeah, this one. For a single process, you should be able to define this pseudocode and explain. So there will be only two processes involved for the Peterson solution. And if we say Pi and Pj are the two processes, then this is the structure of Pi process. So whenever a process wish to execute its critical section, so it should first make turn to itself, that is turn equal to I. This is the structure of Pi. This is the structure of process Pi. So here two variables will be used. One is the turn variable and the other one is the flag variable. So turn will be set to the process who wish to execute the critical section, and flag will be indicating if that particular process is interested in entering the critical section. That's a boolean variable. So using these two variables, the structure of Pi and Pj will be defined, and you can just write the structure of only one single process, that is Pi. Only this particular pseudocode you can just define. So while the condition is true for a particular process, that is the flag condition, we are speaking with regard to the flag condition, and then turn, it will set it to itself, and then we are checking the condition while turn double equal to j and flag, that is if flag is also given to j, then this process keeps waiting, that is does nothing. That's what this semicolon represents. Here semicolon represents no operation. So this process Pi does nothing and keeps waiting until the neighbor process, that is Pj, completes its critical section. Until that flag of Pj becomes false, this process will keep on waiting, and once this condition fails, that is this while condition fails, then this process Pi enters its critical section, and once it completes executing its critical section, it will set back the turn to the neighbor process, and then this process Pi continues with its remainder section. So we have already discussed that critical section is nothing but whatever the code that contains the shared data modification, the shareable resources access, that part of code we consider it as critical section, and rest of the code where no shareable resource is being involved will be considered as the remainder section. So executing remainder sections simultaneously by any process or by any number of processes doesn't have any effect, whereas if more than one process tries to access the shareable resources, then there comes the problem, that is it leads to inconsistency. In order to preserve the consistency, we need to ensure that the shareable resources can be accessed by only one process at any point of time. In order to ensure consistency, we need to ensure that shareable resources can be accessed by only one process at any point of time. So for that reason only, we are dividing the entire code of a process into two regions, critical region and the remainder region. So critical region is nothing but the piece of code that involves the shareable resources. On the other hand, other than the shareable resource code, we consider it as remainder section. So our agenda is to ensure that no two processes are going to execute their critical section at same time. This is what our main agenda. No two processes should enter their critical sections at same time. So if any process have begun executing its critical section, then all the other processes who wish to execute critical sections should be kept waiting. Should be kept waiting, because already one of the process have entered into its critical section, which indicates that it is going to modify the shareable resource. So at the same time, we cannot allow other processes who also wish to enter the critical section to be entered. So for that reason, the main agenda is to restrict two processes entering their critical sections at same time. And this Peterson solution is an example of a software-based solution. It's an example of software-based solution, and it is restricted for only two processes. So this is also one of the expected question. So you just need to explain that it is software-based solution and it is very ancient technique. It is restricted for only two processes, and it is the best solution for representing the cooperation among the neighboring processes. And you need to define the structure of one process pi like this, and you need to explain the purpose of the flag variable and the turn variable, and then you need to end your answer with specifying the limitations with such software based solutions. The first and foremost solution you can just mention is that this particular solution is restricted for only two processes, and the second solution, second limitation that you can mention is that since it's a software based solution and they can be delicate, so these are the two key limitations that you can specify after explaining the solution. And coming to the advantages, yes, it is very much protective in terms of two processes only being involved. That's the key advantage. So not much lengthy code being involved for ensuring this particular synchronization. So that's what the advantage you can just specify. And coming to the hardware based solutions of this synchronization, you can just mention the lock mechanisms. So explain the mutex locks, and using the mutex lock you can just specify how this particular synchronization is achieved. And coming to the OS based solution, you can just explain the semaphores and monitors, and try to explain the types of semaphores as well, that is the binary semaphore and counting semaphore. That also you just need to explain with regard to the semaphores. And as mentioned, go through the classic problems of synchronization, that is the producer consumer problem, which we have seen under the bounded buffer problem, and then the readers writers problem and the dining philosophers problem, and go through the solutions of all those classic problems using both semaphores and monitors. You need to be familiar with the pseudocode compulsory. So without pseudocode you might be losing your marks. So make sure that the solution using semaphores and monitors pseudocode is also known to you. And then, yeah, as said, coming to the CPU scheduling algorithms, I think without arrival times everyone is familiar, but still let's go to that particular. And whatever the scheduling problem you get, I recommend you to explain this scheduling criteria. So explain the these 5 points with regard to the scheduling criteria, whether asked or not. I recommend you to explain the scheduling criteria for any scheduling problem being asked. So mention these 5 scheduling criteria. So CPU utilization, which means that keeping the CPU as busy as possible. And then throughput, it is the number of processes that are completed per unit time. And turnaround time, the amount of time to execute a particular process. Waiting time, the amount of time a process has been kept waiting in the ready queue. And response time, it is the amount of time it takes from the request being submitted until the first response produced to the end user. So these are the 5 scheduling criteria you just need to explain, and make sure that you also specify which is to be maximized among these scheduling criteria and which is to be minimized. I think you are familiar with that. So among these 5 scheduling criteria, we need to maximize the CPU utilization and throughput. Remaining all 3 should be minimized. Only the utilization and throughput should be high. Remaining 3 should be low. So keep that in mind. And coming to the CPU scheduling algorithms, we have discussed about the preemptive versions and the non-preemptive versions. So preemptive versions means forcefully stopping an on process and giving chance for the other process. So forcefully stopping the process that is currently in execution and giving chance to the other process that is in the ready queue. So that's what preemptive scheduling. On the other hand, non-preemptive scheduling means, so you are not going to forcefully stop any process that is already in execution. So no forceful stopping of any process that is currently in execution. That is what the non-preemptive scheduling. And coming to the non-preemptive scheduling versions, we have discussed that FCFS, that is the first come first served, and the SJF, shortest job first. These are the two non-preemptive schedulings we have discussed. And then coming to the preemptive versions, round robin, of course, it's always preemptive scheduling only, because we are going to set some time slice, and based on the time slice that you are setting, immediately you are going to forcefully stop the ongoing process and you give chance for the next process in the ready queue. So that's what the round robin scheduling is. And then priority is also in somewhat it is preemptive version if arrival times are given. If arrival times are not given, definitely you are going to rearrange the processes with respect to their priority decreasing order, and the highest priority will be executing first and the least priority process will be executed last. So with arrival times given, priority also will be a preemptive version, will become the preemptive version, whereas without arrival times, then the highest priority process will be executing first and the lowest priority process will be executing last. And coming to the shortest job first, we always consider it to be non-preemptive version with the shortest requirement, that is the shortest burst time process will be executed first, whereas the largest burst time process will be executed last in shortest job first. But coming to the preemptive version of shortest job first, we call it as SRT, that is the shortest remaining time. So the preemptive version of SJF comes into picture only when arrival times are given. Only when arrival times are given. So these things you should be familiar with. So here, whatever might be the scheduling algorithm you are doing, make sure that you draw this Gantt chart, this particular, observe the mouse cursor, this particular diagram we call it as the Gantt chart. So always make sure that you are going to draw the Gantt chart and illustrate properly all the numbers indicating when a particular process have begun and when a process have ended, and all that you just need to mention. And don't get confused while representing the table with respect to the turnaround time, because turnaround time is not the exit time. Always do remember the fact that exit time minus arrival time will be your turnaround time. This point to be noted, because most of the times when arrival times are given, drawing the Gantt chart, people might get confused with the exit time or the finish time as the turnaround time, but that's not the situation. So you need to always do remember that whatever the Gantt chart you are drawing and whatever the timelines here you are seeing, they are the finish times or the exit times. They are not the turnaround times. They are not the turnaround times. They are just the finish or exit time. So when you subtract the arrival times from the exit time or finish time, then only you get the turnaround time. So this point to be noted very much. And coming to the waiting time, so once you find the turnaround time, then it is very simple for you to calculate the waiting time, because whatever the turnaround time you mention, if you subtract the burst time from the turnaround time, you get the waiting time. So always do remember these points while you write down the table, because initially you will be given only these two columns, and if arrival times are given, one more column will be included. So only the process, burst times and the arrival times will be given to you, and then you need to fill the remaining two columns, that is the waiting time column and the turnaround time column you need to fill. So when arrival times are given, as said, the exit time minus the arrival time, you get the turnaround time for a particular process, and turnaround time minus the burst time, you will be getting the waiting time for that particular process. So just remember these formulas, so that given any problem with any number of processes and with a different burst times also, you would be able to easily calculate the average waiting time and average turnaround time for any scheduling algorithm. So here in this particular PPT, I hope you have already downloaded all these PPTs as said in yesterday's session. So in this chapter 5 PPT, you will be able to find the uh, FCFS and then the SJF and the round robin and the priority without the arrival times. So with arrival times, here I have just taken a one small problem for you to make you understand. So you can just have a look at this particular problem. So this is the preemptive version of SJF, which is nothing but the shortest remaining time. So when arrival times are given, and if you are asked to find out the shortest job first, indirectly you are asked to find the preemptive SJF only. So always do remember that, and don't get confused when arrival times are given. So when arrival times are given, your SJF becomes SRT. Without arrival times, SJF is straight away rearrange the processes with respect to ascending order of burst times. Without arrival times, straight away you can rearrange your processes in the increasing order of burst times, and then straight away you can just find out the turnaround times and waiting times. So when no arrival times are there, your finish time or the exit time itself is going to be your turnaround time. When no arrival times are given, your finish time or exit time itself is your turnaround time. But when arrival time is given, compulsory your turnaround time is going to be finish time minus the arrival time. So here I have just taken a small example. I hope you can understand from this particular example. Here I have drawn the Gantt chart also. So P1, P2, P3, P4 are the 4 processes having burst times 21, 4, 2, 6 respectively, with arrival times as 0, 1, 2, 3 for P1, P2, P3, P4. So these things will not be given in the problem. This I have just represented directly here from this Gantt chart. So coming to the Gantt chart, at 0th second, P1 is the only process that is readily available. So P1 begins its execution, and after P1 executes for 1 second, at the end of first second, P2 is arriving, whose requirement is just 4 seconds, and P1, which began its execution, actually requires 21 seconds, and at the end of first second, P1's requirement is 20 seconds. But P2, which is readily available at the end of first second, has requirement of only 4 seconds. So P1 to be stopped and P2 to be started. So P2 is getting started, and after P2 executes for one more second, that is at the end of second second. After P2 executes for one more second, that is at the end of second second. So here you can see who is arriving. So at the end of second second, so you are seeing P3 arriving, whose requirement is just 2 seconds, and current ongoing process P2, after executing for 1 second, still it requires 3 seconds. So here P3's requirement is less, so P2 will be preempted and P3 will be serviced. So P3 will be starting at the end of second second, and after executing for one more second, so P3 will be completing 1 second and remained with 1 second, but the process that is incoming at the end of third second has a requirement of 6 seconds. So P3 need not be preempted after executing 1 second, so it can complete it 2 seconds. So at the end of fourth second, P3 will be totally completed, where P1 and P2 are still yet to complete their remaining time. So at the end of fourth second, we have 3 processes awaiting. So P4 is also ready with a requirement of 6 seconds. P2, which is preempted when P3 arrived, has requirement of 3 seconds, and P1, which is also preempted, has requirement of still 20 seconds. So among all these 3, P1 requires 20 seconds, P2 requires 3 seconds, P4 requires 6 seconds. So we are giving chance for P2. So P2 completes its all 3 seconds. So at the end of 7th second, P2 is completing its execution. And at the end of 7th second, we still have 2 more processes yet to finish. That is P4, which requires 6 seconds, and P1, which requires 20 seconds. So P4 has shortest remaining time. So P4 will be given chance. So it completes all its 6 seconds. So it completes by 13 seconds. and at the end of 13 seconds we have only one process, that is P1 to finish. So P1 finishes all its 20 seconds, so it completes by 33rd second. Now coming to the turnaround time, so here as mentioned, whatever from the Gantt chart you see, they are the finish times. So when you are writing the turnaround time, make sure that you subtract the arrival time from the finish time. So here coming to P1, its arrival time is anyway 0, so its exit time, that is 33, is becoming its turnaround time. Coming to P2, P2 have exited actually at 7th second, but among these 7 seconds, it have arrived only after first second. So 7 minus 1, you get 6 as the turnaround time for P2. Likewise, P3 have exited at 4th second, but it arrived actually at only after 2 seconds. So 4 minus 2, you get turnaround time of P3 as 2. And lastly P4, which actually exited at 13th second but arrived at 3rd second. So 13 minus 3, we get 10 as the turnaround time for P4. And coming to waiting times, once you find the turnaround times from the Gantt chart, it is easy for you to predict the waiting times, because waiting time is nothing but turnaround time minus burst time. So 33 minus 21, you get waiting time for P1 as 12. And coming to the P2's turnaround time is 6. Out of these 6 seconds, 4 seconds it have executed. So the balance 2 seconds only it has been waiting. Likewise, P3, whose turnaround time is 2, and all those 2 seconds were being executed by P3. That means P3 did not waited. So P3's waiting time is 0. And lastly, P4, whose turnaround time is 10, out of these 10 seconds, P4 have executed for 6 seconds. That means the remaining 4 seconds it has been waiting. This is how you are going to get. And once you find this table, it is easy for you to calculate the average waiting time and average turnaround time. So compulsory you need to end the problem by writing down the average waiting times and average turnaround times. Don't forget to do that. So not just drawing the Gantt chart and filling this table, but also you need to write down the values for the average wait time and average turnaround time. So this is how you are going to calculate the average waiting time and average turnaround time if arrival times are given. And this I have said you for SJF, and similarly you can also do it for priority also. The only point need to be understood here is, when you calculate the turnaround time, always do remember the formula that finish time minus arrival time, you get the turnaround time. And waiting time, it's the same formula, turnaround time minus the burst time. So that's how you are able to find the table. And yeah, so as mentioned, one of the compulsory expected problem from this process management is the CPU scheduling algorithm. So CPU scheduling algorithm is one problem that you can expect, but with arrival times or without arrival times, it purely depends on your luck. And coming to the second half, that is the concurrency and synchronization. So all the 3 classic problems of synchronization, kindly go through the problem statement also. So producer consumer problem, which comes under bounded buffer problem, readers writers problem, and the dining philosophers problem. So go through all those 3 problems. And then as mentioned, semaphore, even though you might be familiar that it's an integer variable whose value can only be modified by 2 atomic operations, wait and signal. So these are the few definitions that we have already discussed. So semaphore is basically an integer variable whose value can only be altered by 2 atomic operations, wait and signal. So wait will decrement the semaphore value, whereas signal will increment the semaphore value. So whichever process wish to access a resource is going to first execute wait on a semaphore value, and then after it completes the use of the resource, it has to issue the signal operation on the semaphore value in order to make it available for other processes. So explain the both binary and the counting semaphores. So binary semaphore means when you have single instance of a resource. On the other hand, counting semaphore represents the multiple instances of resource. So the count value of a semaphore is dependent on the number of instances of a resource you have. So that's what the count will be initialized, and whenever the semaphore value is less than 0, it indicates the resource is not free. Then all the processes that execute wait operation will be kept waiting, and whenever the semaphore value becomes positive, then the waiting processes will be notified, saying that one of them can be able to successfully execute the wait operation again and use that particular resource. So this is what you just need to explain with regard to semaphores, that is both binary and counting semaphores. And then you need to also remember the limitations of the semaphores. So the key limitations of semaphores is compulsory. When the programmer writes, it must and should follow the sequence, that first wait to be executed and then the signal operation to be involved. If signal is written first before the wait, then it is going to be a blocked stage. So this is one limitation, and another limitation is if wait or signal omitted in the code. That means by mistakenly if wait or signal statement is missed in the code, that is also a limitation. So all these limitations of semaphores also to be studied well. And then coming to the monitors, one advantage with monitors is rather than blocking the entire process, here you have the conditional wait and conditional signal. So in monitors, then the one advantage that you have than compared to semaphores is the, here with monitors we have the advantage of conditional wait and conditional signal. Rather than blocking the entire process, we are going to divide separate conditions, and conditionally we are going to keep waiting a process or anything. So that conditional wait and conditional signal will improve the performance of the system, and the throughput also will be improved than compared with the use of semaphores using monitors. And then the message passing technique. So message passing, I don't think you might be getting it for long question. So it's generally a short question only, since you don't have now part A questions, so you can just skip that. So these are the main questions that you can expect from Unit 2. So one is the CPU scheduling problem with or without arrival times, and the other one is the Peterson solution or the semaphore solution or monitor solution for any of the classic problems. I hope this is clear with regard to Unit 2 revision. So in next session we are going to discuss the important questions for Unit 3. Thanks for attending the session and have a good day.